Hello, welcome to this being part 10 of our acid-base equilibria discussions. And you may be thinking to yourself, there's just no end to this acid-base. Yeah, it does kind of seem like that. But the reality is that really there's no new learning for the most part after just the first couple of videos, the videos on strong and weak acids and bases. But there's a lot of different things that gets done to those, and a lot of different ways that it acts. And so it's important to sort of cover the wide range, and also this is covered a lot on the AP Chem exam. So an important one to just make sure it's thoroughly covered. This is the idea of like predicting pH. Are we going to have an acidic solution? Are we going to have basic solutions from common salts? So you get all sorts of salts dissolved in stuff, and it causes the solution to become acidic or basic. And there's a way to know how much it's going to cause it to be. So there's a way to know whether it's going to be acidic or whether it's going to be basic. So sort of the basic understanding works like this. Neutral ions, which are the particular ions that are grouped with our strong and weak bases, they don't cause any pH change. They don't have any effect on pH whatsoever. So if I've got my group 1, that's what this is supposed to say, my group 1 cations, so we're looking at lithium, sodium, potassium, rubidium, cesium, all of those plus these couple of group 2s, or these 3 group 2s, calcium, strontium, barium. When these are in solution, they don't affect the pH at all. But anions over here also don't. And so we have a whole bunch of cations and anions that you have to sort of keep in the back of your mind, as these will not affect the pH. And so if they're in there, you sort of just ignore them, really. So here's our anions, and these are the anions that go with all of our strong bases, right? So these, of course, also don't affect the pH at all. So here's the question then. If I was to have a solution of sodium nitrite, so sodium nitrite, it's not one of my strong base anions, so nitrite is going to cause the solution to become what? Acidic or basic? That's what we want to know. Is this solution going to be acidic, or is it going to be basic? It's a really, really easy way to tell. If you have an anion, right, that is not one of your neutral anions, it's going to cause the solution to become basic. So anions that are not neutral ions cause basic solutions. Cations that are not neutral solutions cause acidic solutions. Right, so for example, iron would cause an acidic solution, whereas sodium won't, because sodium is one of our neutral cations over here. Right, so cations typically cause acidic solutions, anions typically cause basic solutions. So let's look at what happens if I draw this out. My sodium nitrite, when I dissolve that in solution, it's going to become 2 ions, right? We're going to have the cation sodium and the anion nitrate. Well, we know that this isn't going to contribute to the acidity at all. But we know that this has the potential of combining with water molecules, and what will it do? Well, it's not going to turn it into an acid. It has no hydrogens to donate. So it will take an hydrogen, though. And so when it takes a hydrogen, it will become nitrous acid. So essentially, this is our base, even though it's just a simple anion, and this is our conjugate acid. Right? And because it takes a hydrogen from the water, it creates a hydroxide ion, which is what causes our basic solution. And so then the question might become, what is the base ionization constant of this? And that's something you can easily figure out. How can you figure it out? Well, this is a base with a conjugate acid, and we know that bases and conjugate acids multiplied by each other always equal the water ionization constant, which is 1.0 times 10 to the negative 14th. So all we really need to do is figure out, well, can I look up any information? Is there any information readily available? Well, this is a weak acid, and this is called nitrous acid. So you can look that up, like in your back table on page 1115 in your books. Appendix D. So this right here is the answer you get. 4.5 times 10 to the negative fourth, and that's the Ka. Well, it's simple now because all we have to do is plug it into our equation right here for our conjugate acid-base situation. And so we're going to divide 1.0 times 10 to the negative 14th by this and find out that our Kb is right here. So not only can you tell that this is going to create a basic solution, you can actually calculate the base ionization constant of sodium nitrite. All right, let's do one more example real quick. How about an aqueous solution of methyl ammonium chloride? So methyl ammonium chloride is CH3, should be NH3, Cl. Sorry, I messed that up earlier, I suppose. And so what does that mean? Well, it's a combination of a methyl group, which is a CH3, simple one carbon with 3 hydrogens. That's going to combine with an ammonia. And the combination of those is going to create a positive ion. And then it's going to combine with one negative chloride. So here's kind of what you get. You get this right here. They combine to sort of form the positive one of this. And then this, of course, is the negative one. And so when this dissolves, it creates these two ions, the positive methyl ammonium and the chloride ion. All right, so what about these? So what we know is that chloride is one of my strong acid, hydrochloric acid. It's one of my strong acid anions. So this is not going to contribute to the acidity of the situation. And the question, see it's right here, the question might be, is this going to become basic or is this going to become acidic? Well, it's really easy to tell that right off the bat because we know that this is our positive and we know that our negative doesn't affect, it's a neutral. So if we've got a positive, remember positive cations create acidic solutions. So the solution is definitely going to be acidic. And so then could we calculate a Ka? Because if we know it's going to be acidic, then the next question might be what is the Ka of this solution? What is going to be the acid ionization constant of methyl ammonium chloride? Well, methyl ammonium chloride, when it dissolves, is going to turn into the chlorine and then the methylamine, or I mean the methyl ammonia ion. And so in the presence of water, what's going to happen is it's going to actually donate one of those hydrogens. It's going to donate to the water, right? So it's going to create our hydronium ion, and it's going to become the methylamine molecule right here. So here's methylamine. Now methylamine is one that you can look up. You can look up methylamine. So oftentimes when you're doing these salt things, whatever they become when you put them into water, remember if they're positive, they're going to make an acid. If they're negative, they're going to make a base. And you can look it up. So we know that this right here is going to be basic because this is our acid and then this is our conjugate base. So we can look this up, and we find in the back of your books on the next page on 1116 you find that it has a Kb of 4.4 times 10 to the negative 4. So same thing, plug that into our Kw equals Ka times Kb, and you can quickly solve for the Ka of methyl ammonium chloride solution. All right, so hopefully that helps with sort of sorting out the situation with salts and how to figure out whether they create an acidic or a basic solution, and then being able to solve for their respective ionization constants. All right.